All right, welcome back. So, when magma cools underground, it creates intrusive igneous rocks inside the Earth. When that magma reaches, is near or at the surface and cools and solidifies, it forms what are known as extrusive igneous rocks, rocks that have formed by lava exiting the Earth. All right. So when that happens, the magma or lava cools and crystallizes. So the process of crystallization is whereby mineral grains form and grow in cooling magma or lava. So when we're looking at an igneous rock, one indication you have a possible igneous rock is a bunch of little pieces of crystals, kind of just all stuck together. The rate at which the lava or magma cools determines the texture of the rock itself. So if the molten material cools very quickly, like lava would when it hits the surface, cools very quickly, then you're creating rocks that only contain very small crystals. It cooled so quickly that the crystals, as the material began to cool and solidify, didn't have time to grow. Whereas slow cooling over long periods of time creates large crystals. So as that hot molten material is bubbling up through the earth, but stops, doesn't quite make it to the surface, it takes a long time to cool down. It's much warmer in the earth, so it takes a longer time to cool down, allowing for the crystal grains to grow in size. So, if we're talking about small crystals, then we're talking about something called aphanitic texture. Breaking down that name, it's a Latin term, a meaning not, phaner, the root of that meaning visible. So these are igneous rocks that do not have visible crystal grains to the naked eye. These are what are known as volcanic igneous rocks or extrusive igneous rocks. They have small crystal grains that we can't see with the naked eye, maybe with a microscope, because they crystallize very rapidly on Earth's surface. So we know that they were formed when molten material left these confines of the Earth. So again, small crystals. The crystals aren't distinguishable by the naked eye. You need magnification, whether it's a little magnification, magnifying glass, or even microscope. Sometimes that could help. But again, these form on the surface of the Earth. We can tell that just by looking at and noting that they have small crystals. Examples of extrusive igneous rocks include basalt, andesite, rhyolite, just to name a few. So again, we're talking about extrusive igneous rocks that formed on the surface of the Earth. For instance, like basalt and rhyolite. If magma, molten material below Earth's surface, cools, then it has a phaneritic texture. Phaner meaning visible. So these you can see the individual crystal grains. These are also known as plutonic or intrusive igneous rocks. Pluto being the god of the underworld. They crystallize very slowly. It's a little bit warmer underground, so that it's a longer time to cool down, so the crystals can grow a little bit larger. You can typically pick out the individual crystal grains with the naked eye. Some examples of intrusive igneous rocks include gabbro, diorite, and granite, just to name a few. So this is going to be magma that cools below ground, can give you, larger crystalled intrusive igneous rocks like gabbro and granite. For instance, granite, you can pick out the orange and the black and the white. You can see the different crystal grains. Looking at basalt, with a magnifying glass, you can see it's made up of very tiny little crystals, but to the naked eye, it kind of just looks like a black, solid, solid black, matte black rock. So, the difference between an aphanitic texture, non-visible crystals, and a phaneritic texture. Again, you can pick out the white little material here. You can see the black crystal grains, the pink crystal grains. You can pick them out. We're not looking at giant chunks of crystals, but just in grains of crystals. And the crazy part is, these two things are made of the exact same stuff. It's the exact same material composition in the molten rock. It's just the phaneritic textured igneous rock. This is granite. That magma cooled underground, so it's an intrusive igneous rock. That same material, if it made its way to the surface and cooled very quickly, giving it an aphanitic texture, forms rhyolite. Rhyolite and granite are the exact same stuff, made of the exact same stuff. Just one cooled below ground, one cooled on the surface. Bigger crystals below ground took longer to cool. Smaller crystals on the surface took longer to cool. Or shorter, or less time to cool, excuse me. Before we go on, let me give you part of the super secret code. This is the number 9. You got it? 9. One more time, the number 9. Some additional igneous rock textures. There's a glassy texture. Igneous rock will have a glassy texture if lava on the Earth's surface is cooled very quickly. So quickly, crystallization cannot occur. When it's cooled so quickly, you create a natural type of glass with few or no crystals. A good example of an extrusive igneous rock with a glassy texture would be obsidian. Vesicular has vesicles, holes, air bubbles. It results from gases trapped in the molten material at the time of solidification. Also associated with very quick cooling because it's got those gas bubbles trapped. Some example of some extrusive igneous rocks with a vesicular texture would be pumice and scoria. So here's a glassy igneous rock texture. Looks like a chunk of broken glass. Here is a vesicular igneous rock temperature. You can see the little holes, the little vesicles in here. And most likely when you're seeing these, both indicates extrusive igneous rock. So it tells a story. It's not necessarily picking it up and saying, oh, it's this type of rock. But looking at it and saying, oh, it has holes. It must have contained a lot of gas bubbles and cooled very quickly. Therefore, it cooled on the surface of the Earth. It tells a story. So not only their texture tells a lot about where they formed, their color gives us indication of the chemical composition, which indicates where the magma originated from that formed these rocks. So igneous rocks are typically subdivided into 3 categories based on the silica content. Felsic igneous rocks are rocks rich in silicate minerals that contain lighter colored elements like silicon, oxygen, aluminum, sodium, potassium. Therefore, they're lighter in color. So if we're looking at an igneous rock and it's lighter in color, that's telling me it's rich in silica. Therefore, that magma kind of melted kind of from the upper reaches of the crust mantle area, kind of higher up. Intermediate composition igneous rocks have a mixture between felsic and what comes next, mafic. All right, mafic igneous rocks are rocks not rich in silicate minerals that contain heavier elements and darker elements just in color, like magnesium, iron, and calcium. They are darker in color and they come from lower in that crust mantle kind of interaction. So the color of an igneous rock tells us where the magma came from. So if I'm looking at an igneous rock and it's darker in color, black, well, that magma material came from deeper down in the crust mantle boundary. Whereas if I'm looking at a igneous rock that's lighter in color, that magma came from a little bit higher up, more towards the crust. Intermediate, it's like a grayish color, kind of maybe in between. All right. So now we can indicate and identify rocks by their texture. Fine-grained, aphanitic rocks, coarse-grained, those are bigger-grained, phaneritic rocks, glassy texture, vesicular texture, but also their composition, mafic, intermediate, or felsic, and a quick check on whether it's mafic, intermediate, or felsic, if darker colors versus lighter colors. So then we can also tell where the magma came from that made this rock. So you can pick up a rock, and it just tells you a good story, a good story. So we also find in geology not only rocks, but igneous material, magma as it cools below ground. It forms these different patterns as that hot magma is making its way, cutting through the layers of the earth. Again, underground, if that material cools, depending on the shape of how it cools, the size of how it cools, the direction of where that magma material is going, it will give us different structures like batholiths and stocks are just big cooled bodies of igneous material. Laccolith, if it kind of forms like a mushroom shape. But then we also have dikes, which are kind of vertical intrusions of igneous material. We also have sills, like think a window sill that goes sideways, connection of igneous rock. So yeah, so just another kind of image of it. Dikes and sills kind of typically, they're long planar features. They're not just kind of a tube of material typically. All right, so that's just a brief introduction to igneous rocks. We'll look at more of those in lab when we're talking about textures, composition, mafic, felsic, etc. So we'll take a look at all of that a little bit more in lab. But for now, we'll pause here. When we come back, we'll talk about some of the hazards associated with igneous material as it reaches the surface and exits the earth, comes onto the surface, some of the hazards associated with that material. See ya in just a minute.